Hello, ni hao. My name is Eric Tschetter. I'm the creator of Druid. I only know, well, 3 words in Chinese, ni hao, xie xie, and wai ni. But that last one doesn't really have much place in a presentation. But I'm here to talk to you today about Druid. It is an open source data analytics system that I started at a company called MetaMarkets. We're a startup based out of San Francisco working in the internet advertising analytics space. Normally, I start out with a demo of our product. We were just trying to get the internet to work, and it wasn't wanting to cooperate. So I will have to skip the demo. But to give you an idea of what the product does, we provide a dashboard on top of internet, the advertising auction. And so every time an ad gets shown, there's an auction that happens in some marketplace somewhere. There's demographic data associated with the auction, like gender, age, intention of the user. There's also the page that it's showing on, and various other dimensions like that people want to be able to slice and dice their data by. Now, the auction marketplaces, the auction houses, they have sales teams that try to sell inventory. They try to sell to websites and as well as to advertisers the need for using them. And in order to do that, they require data. And they require understanding the demographic breakdown, understanding the current cost of the inventory, understanding the current cost of the ads on the system, and explaining that to users. And the product that MetaMarkets offers gives them the ability to drill down and slice and dice and explore the data as salespeople talking to their customers. And what I'm going to talk to you today about is Druid, which is the infrastructure that we developed to support the product that MetaMarkets offers. And that infrastructure is open, and you can all use it. Now, the presentation today is going to be, first, I'm going to start out with where we started, why we ended up building Druid, because Druid is kind of another database. It's and every time you think about databases, everyone always wonders, why are you reinventing the wheel? Why are you redoing something that everyone has already done? And so I'm going to take you through the story of why we ended up doing this and end with a kind of high-level overview of what Druid is, how it works, and give you some ideas for whether or not you might want to use it for whatever problems you're running into as well. And so I'm going to start out with the requirements that we had for our product. And the first one is data ingestion. This is how quickly can you get data in, and I represent it by a bunch of brides eating cake as quickly as possible. But data ingestion was very important to us. Being able to drill down into the data or slice and dice and cut up the data in whatever format you need. And also availability. MetaMarkets is a software as a service company, meaning that we have to provide our product 24 hours a day, 7 days a week. We can't take downtime. We can't do anything like that. A lot of analytics systems are built with the understanding that the users are internal business analysts. And so they go home at 5 p.m., they go home at 6 p.m., and you can take downtime overnight. You can take downtime, update things, bring it back up in the morning, and that's fine because they won't notice the difference. For us, we can't do that, and so we had to build a system that is available, that we can update without taking any downtime. And so to reiterate the requirements kind of in text, one is the data ingestion rate. We needed to get lots of data in quickly and make it queryable and visible in real time. We also wanted to allow for arbitrary slicing and dicing, arbitrary Boolean filtering, so that you can analyze and investigate the data in any way that you need. And also availability. No downtime. Downtime is evil. So with those requirements, first, what we tried. One thing everyone probably goes to if you have this sort of problem is a relational database. You start out with some relational database. We picked something off the shelf, and we started putting data into it. We set up the data in a traditional BI setup. We had it set up in a star schema. We had a number of aggregate tables on top of the data, and we had a query caching layer, so that if you issue a query and you've already issued it before, you get the exact same results back. And so we had this running, we had some customer data in it, and the results of it were that queries that were cached were fast. As you can imagine, anytime you're accessing a cache, it's fast because you're not actually computing anything. Queries against the aggregate tables were generally fast to acceptable. It was fine. We were getting an experience for our customers that wasn't too bad. But anytime we didn't have the data in an aggregate table, anytime we had to fall back to the base fact table and query it, the query speeds were generally unacceptable. Now, what does generally unacceptable mean? This is a naive benchmark of the system we were using. Doing a really simple select count star, we were able to process about 5.5 million rows per second per core. It seems like decent numbers. However, at this time, this was 4 years ago, our largest customer 4 years ago, they served roughly 700, 800 million impressions a day, and they would give us that data in batch. We would summarize that down to about 60 million actual records that we would put into the database for 1 day's worth of data. Now, our dashboard, by default, shows 1 week's worth of data. So we're looking at 7 days, or about 420 million rows of data, in order to answer queries about that 1 week's worth of data. So one query over 1 week at our naive scan rate, roughly 5 seconds on a 16-core machine. That's what was available to us at the time 4 years ago. Now, our dashboard does multiple queries in parallel in order to show data to our customers. Roughly 15 to 20 queries on each payload. So you take 15 to 20 queries, each of them taking about 5 seconds to compute, and you have a long time. It's easily over 1 minute for a single page load. And if it takes 1 minute to load one page, then that means that a salesperson on the phone with a customer can't explore the data. They can't figure out what the actual eCPM, how much money is being made in a specific demographic group and other things like that. We needed it to be sub-second latencies in order for them to actually do their job. And so this was unacceptable to us. So we said, okay, relational databases, no, they're not what we want. What did we move to next? We moved to what everybody moves to when relational databases don't work. We went to NoSQL. And we grabbed a NoSQL store, and we started pre-computing values and putting all of them into our NoSQL store. So what do I mean by pre-computing values? The general setup was that we would take our data on the left here. Let me see if I can get this working. So we would take data like this, and we would pre-aggregate it into keys like this. So if we had, at timestamp 1, a male, age 18, generated 15 cents worth of revenue, timestamp 1, female, age 25, $1.03. We would then aggregate it up so that at timestamp 1, we would truncate the 2 down to a 1 and say, okay, we generated $1.19 of revenue total. All males at timestamp 1 were 15 cents, but females, because there's 2 of them, were $1.04. And so we would generate all of this and basically generate this larger table with results pre-aggregated inside of it. Now, accessing that, it actually is very fast. We basically, when we needed to display data on our dashboard, it was a range scan on the primary key. We were running with HBase, and we set up the key structure so that the time series were co-located, and it just did a range scan in order to serve a time series. It was really fast and nice. The problems came in around flexibility. If we hadn't pre-aggregated it, it wasn't available. One of the things in our experience that we show people is top lists. We want to provide top lists of the top pages that are serving ads, the top demographics that are serving ads, what age group are they selling to, the most and things like that. And pre-aggregating top lists is actually a fairly difficult problem because you don't know how large to pre-aggregate, or you have to do a lot of scanning after the fact, and scans are not necessarily always fast. Another problem, and actually the biggest problem with all of this, was that the processing scaled exponentially. As we added more and more dimensions, the amount of processing we had to do also increased in an exponential manner. And the thing that really hit home for us to describe this is, at one point, our smallest customer at the time, 1 day's worth of data was 500,000 records. So all we had was 500,000 records of data for that 1 day. Now this data set, you can load it up and use grep and awk and those types of tools to process this data set. And you'll get results really fast. However, we were computing all of the dimensional combinations, and initially we had 11 dimensions wide. And that took 4.5 hours on a 15-node Hadoop cluster in order for us to compute the dimensional combinations here. Our customer came back and said, you know, we would like 3 more dimensions. We said, we're not going to limit the number of dimensions that we allow you to see, so yes, we will give you 3 more dimensions. And we bumped it up to 14 dimensions. When we bumped it up to 14 dimensions, all of a sudden, it took 9 hours on a 25-node Hadoop cluster to produce those same results. And all of a sudden, this 500,000 record set was generating over 1 billion keys in HBase. And so the increase in data size just from taking this really small data set and putting it and pre-computing all of these values was just too much for us to handle, and we said, okay, this is not the way we want our system to scale. So we marked that off the options and said, okay, this isn't working either. What do we do now? And anytime you run into this situation where you're trying to use stuff and none of it's working, well, look at why it didn't work. Step back and say, what caused it to not work? And when we looked at the relational database issue, the problem was that scans against the base fact table were too slow. If those could be faster, then that solution would have worked wonderfully for us. With the NoSQL, with the way we were pre-computing everything, it was computationally an intractable problem. If we wanted to pre-compute all of the dimensional combinations, it's computationally intractable. And actually, I was speaking with the guys on the Keeling team earlier, and they've done a lot of cool stuff in order to make that a lot easier to handle. And so I'm sure you guys will really enjoy the conversation coming from them later on today, because I think it's pretty awesome. But I'm going to continue talking about Druid now and say, well, when we looked at this, we said, you know, the scans being slow is an easier problem to handle. That's something that we can do through parallelization. If we can put the data on multiple machines and scan it all at the same time, we can scan it faster. We can probably also take advantage of various other techniques to make it faster, and so that's what we did. And we created Druid. Now the first whiteboard diagram of Druid is this. It's a guy with animals and stuff. Anyway, this is kind of one of the founders at the company was asking me to draw my idea of Druid, and I drew this on a whiteboard, and yeah. Anyway, the key features of Druid are, and you might notice that each of these 1, 2, and 3 line up exactly with the requirements from earlier in the talk. Druid does real-time ingestion. It will pull data in real time and make it queryable in real time. It will allow you to do slicing and dicing, arbitrary dimensional combinations, arbitrary Boolean on top of the dimensions in your data. You can pull it in and do queries across it, and it's available. It's available, it's served metamarkets for 3 years now, basically being constantly up as long as our data center doesn't go down. But yeah, the architecture, I'm not sure if you guys are familiar with these, but this is a show from my childhood, the Power Rangers. The architecture kind of borrows from the idea of the Power Rangers, where each of the Power Rangers individually was strong. They could each fight some monsters, but at the end of the day, a big monster would come at the end of the episode, and all of the Power Rangers would have to combine their forces together in order to defeat that big monster. And that's kind of the idea about Druid. We take a model where we have multiple different server types, and each of them is good at doing one thing. When you combine them together into a system, it's good at doing the whole thing together and doing everything. And so we have pretty strict separation of concerns between the pieces of the system. And so going into that some more, we start with data. This is a stream of data flowing into our system. And the first thing to describe about the system is real-time nodes. So we have nodes whose primary and only purpose in life is to handle a real-time stream. So what they do is data comes in, and it gets buffered up on the real-time nodes. And it's processed, aggregated to a certain degree, and buffered up over time. Every once in a while, that gets persisted to disk, and then it starts buffering up some more. And then it persists that to disk. And after some larger amount of time, it takes everything that's been persisted to disk and merges it together. This is similar to log-structured merge trees, if you're familiar with that in the data processing space. But so it takes all of it, it merges it together, and it hands it off to what we call historical nodes. Now, historical nodes don't touch any real-time stream whatsoever. They serve old data. And so after the real-time nodes have converted the data into so one thing I did not mention, as they persist, they convert the data into a column-oriented format. They index the data, and they compress it. And so basically, they optimize it for query. And so that optimized form gets handed off to the historical nodes on a periodic basis. It's a configurable system parameter, but generally, we set it to about an hour. So the real-time nodes, the separation of concerns here is that the real-time nodes handle 1 hour's worth of data. And that's all they ever have to worry about. They pull in 1 hour's worth of data, and they hand it off every hour. And the historical nodes, they handle everything else. They just hold data and answer queries on it. And the big thing about this, for those of you who have worked with kind of real-time systems in the past, generally what happens is you pull in data, and you process it, and you store it, and you process it. And if all of your nodes do both of these tasks, then what inevitably happens is at some point in time, you're processing a whole bunch of data, and someone does a query, a year-to-date query, a query over the past 5 years. They do some query that causes a whole lot of data to have to be paged into memory, causes a whole lot of data to have to be processed, and as soon as that happens, it steals resources away from the system that's processing the incoming stream. It stops you from being able to handle the incoming stream, and basically the query ends up taking a really long time because it's fighting for resources with the real-time processing, and the real-time processing falls behind your actual stream because it's fighting for resources with the query. And in the end, no one's happy because you don't process the stream fast enough and the query takes too long. And so that's why we've separated these very, very strictly between the two operations. And so now we have this system of a whole bunch of machines, and actually each of them expose a query API. It's the exact same query API between the machines, but we've got a whole bunch of machines, and querying a lot of machines, it's not fun. No one likes doing it. It's a lot of bookkeeping. And so what we do is we have broker nodes that sit in front of the cluster. And these broker nodes basically expose the exact same query API that real-time nodes and historical nodes expose. However, broker nodes understand where the data is. They understand the data topology. And so when a query comes into a broker node, it can make decisions about where to forward that query off to. And so what it does is it forwards the query onto real-time nodes if the real-time nodes have data required for the query. It forwards the query onto historical nodes if the historical nodes have the data. And then it merges the results back and returns those. And so it does what's generally called a scatter-gather across all of the nodes. And that is the basic architecture of the Druid system. So we have our real-time nodes, which only care about handling a real-time stream, persisting it, and handing it off. We have historical nodes that just serve old historical data, answer queries on it, and then there's broker nodes that combine it all together and make it work. So now there's a question, what kind of data are we dealing with? What kinds of data can I put into Druid and have it be useful? And this is an example of the data that MetaMarkets deals with. One thing to note is there's a timestamp column. So in Druid, all data must have a timestamp. It's all event-style data, and it must have a timestamp. Next, we have Publisher, which is the website that an ad is being shown on. These are just some examples here. Advertiser, the person generating the ad to show on the website. There's gender, country. These are demographic dimensions talking about the person who is viewing the ad on the website, the number of clicks that happened, and the amount of money that was made for impressions inside of that group. And so this is kind of what the data looks like. And I mentioned earlier about how we optimize and compress the data to optimize it for querying. So one of the tools we use is column compression. We use dictionary encoding on the columns whenever we're processing it. And so dictionary encoding, first, we separate it into the individual columns. And so we take the publisher column as a single column. And in this publisher column, we notice that there are two values. There's bieberfever.com and there's ultratrimfast.com. We take these values and we assign them IDs. So we say for this data chunk, for this segment of data, bieberfever.com has ID 0. Ultratrimfast has ID 1. And then what we actually store on disk for the column is the numbers. We store an array of 000111, which represents this column. And so if you're familiar with kind of BI and star schemas, this is effectively creating a dim table, a dimension table inside of the actual segment. And so what we're actually storing is IDs, and we're getting the benefit of having fixed size storage and the benefit of getting fixed size storage with also being able to take in data in a human readable format and not expose to the user the fact that they have to join on a whole bunch of dim tables in order to actually get the values out that they want. Another thing that we can do with this to further shrink the size is we convert the values into numbers. But we also know the cardinality of the dimension. And so if the cardinality of the dimension is, say, less than 256, you can represent that in 1 byte. You don't need to store a 4-byte integer in order to represent that number. You can store it in 1 byte, and so we only use 1 byte to represent each of the rows. You could also take that to the extent of if there's only 1 value, you don't even have to store anything because there's only 1 value in there and you know that it appears everywhere. It's not actually an optimization that we've implemented yet, but it's something that could be implemented if that happened a lot. So another thing we do, I mentioned that we index the data. And so for dimensions like this, like publisher, advertiser, gender, and country, we index every single dimension all the time, always. And how do we index it? We index it with bitmap indexes. Now, bitmap indexes traditionally are seen as rather expensive, especially if you have high cardinality dimensions. However, there's been a lot of research into ways to make that not the case. And specifically, their compression algorithms. They all end up being based on run length encoding, or the idea comes from run length encoding. One of probably the most famous one is called EWA, which is Extended Word Aligned Hybrid. What we use, however, is something called Concise, which comes from researchers out of the University of Rome, and it's an iteration on top of EWA. But the idea of bitmap indexes is if I take this column publisher, I know there's 2 values in it. I have bieberfever.com and I have ultratrimfast.com. And so I can know bieberfever.com appears in row 0, 1, 2, and ultratrimfast appears in row 3, 4, 5. So you can imagine a simple sparse array representation of an index where you look up the value and it tells you what rows are in it. Now, if you can take that and convert it into a bitmap. And so you get, in our example here, for beaverfever.com, you get 111000. The ones mean that it exists in that row. The zeros mean that it does not exist in that row. And the benefit of doing this is that when you're doing Boolean operations, you can do bitwise OR, and not operations on the actual bitmap. And so you can figure out Boolean operations by combining the bitmaps without ever looking at any row of data. And so we can resolve a where clause entirely by looking at the bitmaps. We never have to look at rows of data. And a lot of databases, what they end up doing when you provide a where clause is they look at a row. They say, does this match? If it doesn't match, they say, okay, it doesn't match, I'm going to move on to the next. Does this row match? It doesn't match, let me move on to the next. And they keep going like that. We don't have to ever look at data. We only have to look at data that matches the where clause. We never have to look at data that doesn't match because we can combine the bitmaps before we look at any of the actual rows of data. And one of the benefits of the various compression algorithms for bitmaps is that you can actually do the bitwise operations on top of the compressed form. So most of the time, you don't have to decompress the bitmap in order to do the and or not operation. You can just do it directly on the compressed form and get a lot of benefits. So you can compress things down to really shrink the amount of size required. You can do your operations directly on that compressed form, and in general, it does things relatively fast. One of the benchmarks we have around OR queries. So OR queries in databases are usually very slow. If you want to do an OR that includes 500,000 things, most databases won't allow you to specify an in clause in your where that lets you do that. For us, we tried it, just wondering what it would do, and we can OR together 500,000 bitmaps in about 3 seconds. And so if you give Druid a query with 500,000, with an OR clause with 500,000 individual values, it's a crazy query, we can compute that by first doing the OR in about 3 seconds and then look at the data that matches. And so it's just that 3 seconds plus the actual scan. Now, if you're dealing with only 10 things in an OR or something like that, it's actually much faster. It ends up being less than millis, and it just runs and is quite nice. But anyway, this slide kind of goes over the whole Boolean operation. I'll move on to availability. How does availability work in Druid? One, it's fault tolerant. Basically, this is because of replication. Inside of the various pieces and parts of the system, you can have your data replicated so that if you lose a node, you still have it available. You can set the replication factor so that if you lose 2 nodes, you still have at least one of them with it. It will also kind of heal around that sort of stuff, especially the historical data will self-heal as you lose data and pull it back up. We've also been doing rolling deployments and restarts of software for 3 years. One of the things I'm proud of with Druid is that at MetaMarkets, we've never taken a downtime for a software deployment in 3 years. And this is a large-scale data system that's just always up, even when we're updating software. Growing the system basically is starting more processes. You add more processes, you now have more software processing. You have more CPU processing power. You have the ability to pull in more data and work with it. If you want to shrink, you kill processes. You have to be a little careful about how fast you kill processes, but basically you can kill processes and it will rebalance the data and get everything running again. It's generally extensible. There are interfaces that allow you to kind of set up Druid to work with your system, however you work with things. There's something called deep storage that you can kind of plug in whatever you want for. If you have a service discovery mechanism and you want to be able to find Druid via that, there's a way you can plug in and have Druid integrate with your service discovery mechanism. You can even write your own query types and push those into the system. There are a number of different query types, and you can add your own. You can add your own aggregations. And one of the really cool things, in my opinion, but I'm biased, is being able to add extra column types. You can actually add different storage formats for data. One example of this is hyperlog. There's an algorithm, it's an approximation algorithm for approximating cardinalities or approximating unique counts, and it's called hyperlog. And we actually have that implemented natively within Druid. So we have columns that are the hyperlog storage format, and it allows us to basically do approximate unique counts directly off of those columns without doing other things. We also have count-min sketches. They're another approximation algorithm that allows you to approximate histograms and approximate percentiles within the data. And there's a number of other companies that have implemented their own approximation algorithms as column types and push those into the system. Some benchmarks. Naive benchmark, this is also select count star with some time boundary, so similar to the benchmark I showed you earlier, is at 53 million rows per second per core is the rate we can scan at. Our real-time ingestion rate, generally we say 20,000 events per second per node. This varies depending on the data complexity and your hardware. Our highest benchmark has been 250,000 a second, but that's on a data set you'll probably never ever actually see in the real world. I just include the number because it's a big number. Also, cluster size, talking about Druid benchmarks, or at MetaMarkets, the cluster, I believe this is the largest cluster out there right now, even though some of our partners are picking up and potentially going to exceed it. But it represents 10 trillion events. These are 10 trillion impressions, bids, other stuff. Represents that in over 200 terabytes worth of data across 175 machines. We're maintaining a 90th percentile query latency of under 1 second across this data, and a 95th percentile under 2 seconds. And our sustained real-time ingestion rate is 300,000 events per second. Now, 300,000 events per second, just so you know, is roughly 26 billion events per day are pulled into the system and ingested and aggregated and exposed to MetaMarkets customers via a dashboard. As I said, Druid is open source. Some of the use cases are basically it's interactive dashboards. Druid is built as a dashboarding infrastructure. It's built to power dashboards. If you have KPIs, key performance indicators, if you have server metrics or network metrics, these are all meaningful use cases for Druid, and we've seen Druid used in each of these arenas. Some questions or some thoughts. If you ever find yourself saying, I wish I could slice and dice into this data. I just did something. I wish I could see how well it's doing. I wish I could see what the effect is. If you ever wished you could see stuff at a finer granularity, or that you didn't have to pre-can drill downs. You didn't have to define your dimension set that you want to drill down ahead of time. Druid might be a good solution for you. Druid is open. You can read more about it at druid.io. It's written all in Java. The license is GPL v2. We have about 10 companies in production using it right now, and we've taken contributions from about 40 people. And that's it for the talk. So, 谢谢. And